A temple stands unshaken after 1,000 years of earthquakes. This is the forgotten genius of ancient seismic engineering, a silent science embedded in sacred stones from Greece to Japan. By the end of this, you will understand the precise principles that could make our own cities safer. How did builders without steel or computers create structures that outlast centuries of tremors? And what crucial lesson have modern engineers only recently begun to relearn? What does true resilience look like to you? Their structures did not begin on a drawing board, but in the forest. Ancient builders were first and foremost students of the natural world, and they paid closest attention to what survived the storm. They watched how a grove of bamboo would bend almost to the ground in a fierce wind, its hollow stems absorbing the energy, only to spring back upright when the gale passed. They studied the deep, spreading roots of ancient trees, noting how this flexible anchorage allowed the trunk to sway without toppling. In these observations lay a revolutionary idea, one that modern engineering took centuries to rediscover. The goal was not to stand absolutely still. The goal was to move, to sway, to dance with the earthquake, and to return to center when the shaking stopped. This is the profound philosophical shift that underpins everything they built. They sought harmony with natural forces, not domination over them. Imagine the difference between a rigid oak branch in an ice storm and a willow branch in the same storm. The oak, resisting every ounce of pressure, will eventually snap. The willow yields, allows the ice to bend it, and survives intact. Ancient seismic engineering chose to be the willow. This foundational wisdom meant their temples were designed as living systems, partners with the ground they stood upon. They understood something we often forget in our age of steel and concrete, that sometimes the strongest response is not increased rigidity, but intelligent, controlled flexibility. With this mindset of resilience through motion established, we can now walk through the temple gates and see exactly how this philosophy was translated into stone. The first and most critical line of defense was laid before a single column was raised. It began deep underground with an ingenious deception. To protect their temples, ancient engineers did not try to anchor them more firmly to the earth. Instead, they cleverly tricked the earthquake into passing them by. They achieved this through a principle so advanced that our own engineering textbooks only formalized it in the 1970s: base isolation. The idea is simple yet brilliant. You cannot shake what you cannot fully grip. By creating a flexible layer between the ground and the building, the violent horizontal lurching of an earthquake is not transmitted upward into the structure. The foundation moves, but the temple above it sways gently, like a passenger on a smoothly gliding ship rather than one caught in a crashing wave. This ancient innovation took remarkably sophisticated forms. In Japan, the towering wooden pagodas, some over 1,000 years old, often rest their central pillar on a massive, buried stone sphere. Think of it as a giant, polished marble set perfectly in a socket. When the ground jerks sideways, this stone ball rolls, allowing the entire heavy superstructure to pivot and sway independently. In other cases, builders used layers of loose sand and gravel as a foundation bed. During a tremor, these granules shift and flow against each other, absorbing the seismic energy through friction and converting it into harmless heat, effectively letting the ground slide out from under the building without dragging it along. Half a world away, Greek temple builders arrived at a similar solution through different materials. Beneath the majestic temples, archaeologists have found foundations constructed with alternating layers of smooth stone slabs and soft clay. When seismic waves hit, these layers would slide against each other, the clay acting as a lubricated buffer. The terrifying horizontal force of the quake was spent grinding these hidden layers back and forth, while the temple above experienced a far gentler, filtered motion. It was a sacrificial system, a hidden mechanism designed to fail in a controlled way so that the sacred structure would not. This foundational genius raises a compelling question. If the base could move, how did the entire building above it sway as one unified, flexible entity without collapsing? The answer lies not in the foundation, but in the very bones of the structure itself. Above the sliding foundation, the temple's own skeleton was engineered to move. The stones themselves were taught to dance. Walk up to the wall of an ancient Inca fortress or a temple in ancient Anatolia and run your hand over the surface. You will feel no straight lines, no uniform bricks. Instead, you see a chaotic, mesmerizing jigsaw of polygonal blocks, each one uniquely shaped, each face curved and angled to lock perfectly with its neighbors. There is no mortar holding this wall together. The binding agent is pure geometry and immense weight. This is polygonal masonry, or dry stone construction, and it represents a seismic revelation carved in rock. The builders understood that a rigid, brittle wall cemented together would crack under the twisting force of an earthquake. A single fault line in the mortar would become a catastrophic tear, so they removed the weak link entirely. They designed a wall that was, by its very nature, a flexible matrix. During a tremor, these intricately fitted stones are not meant to stand perfectly still. They are designed to do something extraordinary. They can shift, they can sway minutely, they can even bounce against each other. The energy of the quake is not absorbed by a single material until it shatters. It is dissipated across thousands of tiny friction points as the stones grind and settle against one another. And when the shaking stops, gravity and that perfect, interlocking fit guide each block back to its resting place. The wall settles, often with a new, slightly different configuration, but it remains standing, monolithic, and strong. It is a symphony of controlled movement, where every stone is both an individual dancer and part of a cohesive whole. The lack of rigid bonding is not a vulnerability, it is the structure's genius. This principle transforms a wall from a brittle slab into a dynamic, energy-absorbing fabric. But a building is more than just walls and foundations. It is a complex assembly of heavy components. How did ancient engineers prevent the massive, ornate roof from becoming a deadly pendulum during these seismic dances? The answer lies in the hidden joints above. The heaviest part of the temple was not its greatest weakness, but its most ingenious defense. While our instinct tells us to keep weight low to the ground for stability, master builders from East Asia performed a breathtaking act of architectural. They placed an immense mass at the very top of the structure. In the grand wooden halls of China and the towering pagodas of Japan, the roof is not a mere covering. It is the heart of the seismic system. Constructed from thousands of heavy clay tiles layered over a complex wooden framework, these roofs could weigh hundreds of tons. To a modern engineer, this looks like a disaster waiting to happen, a colossal weight perched high above, ready to act as a destructive pendulum during an earthquake. But that is precisely the point. The ancient builders were not creating a dangerous pendulum, they were creating a tuned, stabilizing one. They understood that the key to controlling motion is to work with the physics of rhythm. Here is how it works. When seismic waves begin to shake the base of the temple, the heavy roof, due to its immense mass and height, wants to sway a fraction of a second later than the wooden frame beneath it. This creates a phenomenon called an out-of-phase motion. Imagine pushing a child on a swing. If you push at the exact moment they are moving toward you, you amplify their motion. But if you push just as they begin to move away, you counteract it, slowing them down. The massive roof acts like that perfectly timed, counteracting push. As the building sways one way, the lagging inertia of the heavy roof pulls it back towards center, dampening the overall swing. This is not a static weight. It is a dynamic mass damper, using gravity and timing to absorb and neutralize the earthquake's energy high up in the structure, before that energy can twist and shatter the columns below. This ancient intuition is so profound that it defines modern skyscrapers today. The Taipei 101 Tower in Taiwan, engineered for a region prone to typhoons and earthquakes, has a massive tuned mass damper, a golden steel sphere weighing over 700 tons, suspended near its top. During high winds or tremors, this sphere sways silently in its chamber, counteracting the building's movement in the exact same principle used in a Japanese pagoda's heavy roof 1,000 years earlier. The builders of old turned a potential liability into the structure's greatest asset, proving that sometimes the solution to a violent force is not to resist it with equal rigidity, but to meet it with a calculated, rhythmic counterweight. This reveals a temple not as a rigid sculpture, but as a complex, breathing instrument. Yet, for all this sophisticated engineering in stone and wood, these structures were meant to last centuries. What happened when the ground shook so violently that even these brilliant systems were pushed to their limit? The final, most humble layer of genius was a simple acceptance, and a plan for graceful failure. The true soul of this ancient engineering, however, lies in its ability to bend without breaking. In the forests of Japan and the mountains of China, builders discovered the ultimate seismic material was not stone, but wood. They did not merely construct with timber, they engineered entire skeletons designed to breathe. At the heart of this system is the intricate art of wooden joinery, a technology so advanced it turns a rigid frame into a living, flexible organism. Beams and columns were not nailed or bolted together in a fixed, brittle union. Instead, master carvers shaped complex, interlocking joints that fit together like three-dimensional puzzles. These connections, often using no metal at all, were engineered with a specific purpose, to allow for controlled rotation and flexing. Think of your own knee or elbow joint. It can pivot and bend within a certain range, absorbing impact without shattering. Ancient wooden frameworks were built on this same biological principle. The most famous examples are the elaborate bracket complexes crowning Japanese temples, known as Tokyo. To the eye, they are breathtaking displays of artistic craftsmanship, layered clouds of carved wood supporting massive, sweeping roofs. But their true function is deeply practical. During an earthquake, these intricate brackets do not remain stiff. They compress, they twist, they act as a series of integrated shock-absorbing springs. The entire wooden skeleton becomes a dynamic shock absorber, swaying as a unified yet flexible whole. The energy of the quake is not concentrated at a single weak point. It is dissipated through the gentle, groaning flex of 1,000 wooden joints moving in harmony. This creates a structure that literally breathes with the tremor, inhaling the violent energy and exhaling it as harmless motion. It is a stark, humbling contrast to many modern constructions that rely on rigid materials like concrete, which can hold immense weight when still, but are prone to catastrophic, sudden failure when twisted. The ancient temple does not fight the earthquake to a standstill. It sighs and sways with it, a dance partner moving to a terrifying rhythm and surviving because it knew the steps. This philosophy of resilience through flexibility extended even to the most sacred and delicate elements within the temple walls. Even the objects inside the temple were designed to dance. The ancient builders understood that resilience was not merely a property of walls and roofs, but a symphony performed by everything within the sacred space. They engineered the interior itself to become a network of passive shock absorbers, turning what we might see as mere decoration or furniture into vital components of seismic survival. Consider a large, freestanding column placed not for structural support, but for strategic mass in the center of a hall. During a tremor, this heavy stone pillar would begin to sway slightly out of sync with the rhythm of the building's main frame. Its independent movement would create a counterforce, its inertia tugging against the sway of the walls, effectively dampening the overall oscillation. It functioned like a silent, stationary pendulum, converting the violent energy of the quake into a gentle, contained rocking motion that dissipated harmlessly. The same principle applied to the most sacred focal point, the central statue of a deity. These were not always fixed rigidly to their pedestals. In some traditions, the statue would be placed upon a base carved with a subtle, rounded foot or set upon a layer of sand. This allowed the icon itself to shift and rotate minimally during a quake. This movement served a dual purpose. Practically, it absorbed kinetic energy that would otherwise transfer into the altar and the floor. Symbolically, it created a profound visual metaphor, the deity itself appearing to acknowledge and move with the powerful forces of nature, rather than being an immutable and therefore breakable object. Even functional and ceremonial items played their part. Large bronze bells hanging from beams or heavy woven tapestries suspended from the walls would begin to swing when the ground shook. Their pendulous motion acted as a tuned damper, their mass pulling against the building's sway at a calculated frequency. The gentle, dissonant ringing of the bells and the soft swaying of the fabrics were not chaotic side effects. They were the sound and sight of energy being bled away from the structure's bones. This reveals a holistic philosophy of design that modern engineering is only beginning to fully embrace. The temple was not a container for sacred objects. It was a single, integrated organism. Every element, from the deepest foundation stone to the highest hanging ornament, was part of a unified system for survival. There was no distinction between architecture and interior design, between structure and furnishing, because everything had a role to play in the dance with the earth. This complete integration of purpose is perhaps their most elegant lesson, a reminder that true resilience considers the whole, not just the shell. Yet, for all this brilliance carved in stone and woven into wood, these techniques did not arise from a single mind or a sudden revelation. They were born from a long, slow, and often devastating conversation between human ambition and the indifferent power of the planet. Perhaps the most stunning example of this holistic wisdom is found not in a construction manual, but in the sacred mist of a mountain shrine. The Temple of Apollo at Delphi was not merely built on a random, picturesque slope. Its legendary priests chose this specific location with a foresight that blends the mystical and the mechanical into one. Modern geological surveys confirm the temple sits directly atop a major fault line, a place where the Earth's crust is fractured and unstable. For centuries, this was seen as the source of its spiritual power, for the same fractures released ethylene and other gases from deep within the Earth. Inhalation of these vapors by the oracle, the Pythia, is now believed by scientists to have induced the altered states of consciousness behind her famous prophecies. The site was, in essence, a direct pipeline to the underworld, chosen to facilitate a sacred dialogue. But the genius runs deeper than spiritual theater. That same fractured bedrock, the source of the intoxicating gases, also served a profound and practical engineering purpose. When seismic waves travel through solid, unbroken rock, they move with devastating speed and force. But when those waves hit a zone of shattered stone, a labyrinth of cracks and fissures, something remarkable happens. The energy is scattered. It is reflected, refracted, and absorbed as it bounces chaotically through the fragmented maze. The violent, unified pulse of the earthquake is broken apart into countless smaller, harmless vibrations before it can ever reach the temple's foundations. In choosing this spiritually charged fault line, the builders effectively placed their temple upon a natural geological shock absorber. This was not an accident of faith, but of integrated understanding. The site selection reveals a worldview that did not separate the sacred from the scientific, the spiritual from the structural. The very geological feature that provided the temples, its connection to the divine, also provided the physical mechanism for its earthly endurance. The trembling of the earth was not just a threat to be mitigated, it was the voice of the god to be interpreted, and with profound intelligence harmonized with. At Delphi, the line between the oracle's trance and the temple's stability is beautifully, inseparably blurred. It stands as a powerful testament to an age where survival was not just about building well, but about listening deeply to the whispers of the gods and the groans of the continent beneath them. This principle of working with motion finds its ultimate expression in a soaring, slender structure that seems to defy all logic. The classic 5-story Japanese pagoda should not exist. By every conventional assumption, this tall, top-heavy tower made of interlocking wood, with its massive ceremonial roof, should have been toppled by earthquakes centuries ago. Yet the oldest one still standing was built over 1,400 years ago, and it has weathered countless tremors without fail. This is the pagoda paradox, and its solution reveals an engineering secret so advanced it feels like magic. The heart of the mystery is a single, colossal pillar called the. It runs straight up through the center of the pagoda, from the ground to the apex. But here is the crucial detail. In many of the oldest and most resilient pagodas, this central pillar is not actually attached to the building. It is not a load-bearing column holding the floors up. Instead, it is suspended like a giant pendulum from the very top of the structure, its base hovering just above the ground or resting loosely in a stone socket. During an earthquake, the pagoda's 5 flexible wooden floors begin to sway. Each floor, with its own mass and joinery, sways at a slightly different rhythm. If left unchecked, these independent sways could amplify each other, whipping the building into a destructive frenzy. This is where the free hanging performs its miracle. As the floors sway around it, this massive central pillar, due to its inertia, wants to stay relatively still. It acts as a stationary reference point in the chaos. The moving floors and the stationary pillar create a system of dynamic counterbalance. The energy from the swaying floors is transferred into the pillar, causing it to swing gently in the opposite direction, which in turn pulls back against the floors, dampening their motion. It is a continuous, silent dialogue of push and pull that turns violent shaking into a gentle, contained rocking. This is why adding more stories can enhance stability. Each additional floor adds more mass and complexity to this damping system, increasing the inertia that the central pillar can work against. The building becomes not a rigid tower, but a tuned instrument, with as its resonating spine. It is a breathtaking demonstration that true stability is not about rigid stillness, but about mastering rhythm and countermotion. This ancient insight, carved in wood and tested by time, offers a humbling question for our own age of skyscrapers. What if the strongest thing we can build is not something that refuses to move, but something that has learned how to dance? That same philosophy of intelligent motion was carved into mountains on the other side of the world. In the high Andes, the Inca built monuments to permanence not with cement, but with a breathtaking understanding of geometry. Their walls, assembled without a single drop of mortar, have 6 centuries of earthquakes for one simple reason. They were designed not as rigid barriers, but as unified living sculptures. At places like and you can witness this genius in every stone. The blocks are not uniform bricks, they are unique, multi-angled puzzles. Each face is slightly convex, each edge is beveled, and they fit together with a precision that feels supernatural. The classic test is to try and slide a razor blade between the seams, and it simply will not go. This is not just artistic vanity, it is high-level seismic engineering. By eliminating any gaps or uneven surfaces, the Inca created what modern engineers call a continuous load path. Think of it like a chain. If every link is perfectly forged and connected, a pulling force is distributed evenly along the entire length. But if one link is weak or misshapen, the force concentrates there, and the chain snaps. In an Inca wall, when a seismic wave hits, the energy travels smoothly across the countless, perfect interfaces between stones. There is no single weak point, no pocket of empty space where stress can build up and cause a catastrophic crack. The wall shakes as a single, monolithic entity. The builders amplified this stability with subtle, brilliant design choices. Look closely, and you will see the walls are not perfectly vertical. They taper inward slightly, giving them a gentle trapezoidal shape. This inward tilt lowers the center of gravity, making the entire structure more resistant to overturning. More importantly, at every corner where 2 walls meet, the stones are interlocked in a 3-dimensional zigzag pattern. During an earthquake, a 90-degree corner is a natural failure point, a place where 2 rigid planes try to pull apart. The Inca corner, however, is a woven knot of stone. As the ground shakes, these interlocking stones grip each other, transferring the forces diagonally through the joint and preventing it from unraveling. It is geometry performing as a seismic restraint. This mastery reveals a profound truth, that in an age before calculators or stress simulations, the most powerful reinforcement was meticulous, intentional craftsmanship. Every hammer stroke that shaped a convex surface, Every patient fitting of one unique stone to another was an act of calculated defense. The wall's strength did not come from an added material, but from the perfect relationship between its parts. It was a community of stone, where each member supported the whole, and that whole has endured long after the empire that built it faded into history. The mountains of Peru speak one language of stone, but the volcanic plains of Italy whisper another. While the Inca mastered geometry without mortar, the Romans achieved a different kind of alchemy, creating a liquid stone that could defy time and tremor. Their legacy in seismic resilience is not found in flexible joints, but in the very fabric of their buildings, in a material science so advanced it would not be matched again for nearly 2,000 years. At the heart of this was Roman concrete. Unlike modern Portland cement, which can become brittle and crack under tension, the Roman formula possessed a secret ingredient: ash, a fine volcanic dust from regions like. When mixed with lime and rubble, this ash triggered a slow, long-term chemical reaction. It produced a crystalline glue that filled every microscopic pore, creating a monolithic mass that was exceptionally strong in compression and, crucially, more resistant to cracking. This concrete did not just sit there. It continued to cure and strengthen for centuries, actually healing tiny fissures with new crystalline growth as water seeped through. It was a living, self-repairing material. But material alone was not enough. The Romans combined this miraculous concrete with a revolutionary shape, the vault. Look up inside the Pantheon at that breathtaking, unsupported dome. Its genius is in its curvature. A flat ceiling concentrates stress at its supports, but a dome or a barrel vault channels the immense weight of the roof and itself outward and downward along its curve, distributing forces evenly across the entire supporting wall. During an earthquake, this meant the seismic energy was not focused on a few weak points, but dissipated across a vast, continuous shell. The building shook as a single, incredibly robust unit. The concrete, with its tensile strength, held the shape together, while the shape ensured no single part had to bear an unbearable load. It was a perfect marriage of form and formula. This is why so many Roman aqueducts, bridges, and temples still stand in seismically active regions like Turkey and Italy. They were not designed to sway, but to be so massively, intelligently interconnected that the earthquake could not find a purchase. No single seam to rip open. Their resilience was one of unified strength, a lesson in building not just with better materials, but with smarter shapes that turn weight from an enemy into an integral part of stability. This Roman approach represents a fascinating alternative philosophy, a path of monolithic endurance rather than flexible dance. It prompts a deeper question, with these two great schools of ancient thought, one favoring motion, the other favoring mass. How did this profound knowledge simply vanish from our collective memory? For so long, the Roman pursuit of monolithic strength met its ultimate test in the shifting ground of the East. In Constantinople, where seismic tremors were a constant threat, Byzantine architects faced a monumental challenge. They inherited the Roman love for the dome, a symbol of the heavens, but a solid concrete dome on rigid walls would be a death sentence in their unstable lands. Their brilliant solution was not to abandon the dome, but to teach it how to breathe. They placed these massive stone caps not directly on solid walls, but upon tall, cylindrical drums. Picture a colossal, inverted bowl resting not on a table, but on a hollow cylinder. This drum, often pierced by a ring of arched windows, It created a flexible transition zone, a kind of architectural shock absorber between the static square base of the building and the dynamic curvature of the dome above. The windows were not just for light, they were structural genius. By carving these regular openings into the drum, the architects transformed what would have been a solid, brittle cylinder into a flexible lattice. When an earthquake's waves hit, this perforated drum could flex and deform slightly, absorbing and redistributing the stresses before they could travel upward into the dome itself. It allowed the heavy stone canopy to sway ever so slightly on its lofty perch, a controlled give that prevented a catastrophic snap. The completed in the year 537 is the breathtaking testament to this adaptive design. Its central dome, a vision of light and space, has weathered over a dozen major earthquakes in its nearly 1,500-year life. It has cracked, it has partially collapsed and been rebuilt, but its essential form, the dome on its luminous, windowed drum, has endured. The builders understood that a series of calculated weaknesses, those graceful arches and openings, created a far stronger whole than any solid, unyielding wall. They turned geometry into a dynamic system, proving that resilience in the ancient world was never a fixed formula, but a continuous conversation between ambition, material, and the relentless memory of the trembling earth. The stones of India hold a different kind of wisdom, one written not in flexible joints, but in sacred mathematics. Within the ancient architectural science of Shastra, every temple was far more than a place of worship. It was a calculated resonance with the universe itself. The builders operated on a profound principle, that harmony in form creates stability in substance. They meticulously prescribed every dimension, from the height of the spire to the width of a doorway, using a system of harmonic proportions known as. These were not arbitrary aesthetic choices, they were precise ratios believed to align the human-made structure with the cosmic order, the rhythm of the stars, and the silent music of creation. A temple built to these proportions was thought to become a conduit for spiritual energy, a battery of divine presence. Yet this spiritual intent yielded an astonishing and very practical side effect, a powerful defense against the chaos of the shaking earth. The secret lies in the physics of vibration. Every structure, from a wine glass to a skyscraper, has a natural frequency at which it prefers to vibrate. If you sing the right note near a crystal glass, you can make it hum. If an earthquake sends seismic waves through the ground that match a building's natural frequency, something terrifying happens: resonance. The energy is not just transmitted, it is amplified. Each wave builds upon the last, like perfectly timed pushes on a swing, driving the structure to oscillate with greater and greater force until it shatters itself from the inside out. This is what collapsed countless modern buildings in earthquakes before engineers understood the phenomenon. The ancient Indian masters, through their sacred geometry, were intuitively avoiding this catastrophe. By designing a temple according to the complex layered ratios of, they ensured its natural vibrational frequency was a unique, complex signature. It was deliberately out of sync with the common, simpler frequencies produced by most seismic waves. When the earthquake's monotonous drumbeat hit the temple, the structure could not find its rhythm. The energy could not lock in and amplify. It was scattered, reflected, and dissipated as dissonance. The temple, tuned to a celestial harmony, simply refused to sing the earth's destructive song. This is why you might see a towering, ornate, or spire that seems to defy gravity on unstable ground. Its proportions are a calculated bulwark against resonance. The builders were effectively frequency tuning their temples for seismic safety, using sacred math as an invisible shield. It represents a breathtaking convergence where spiritual aspiration and physical survival were seen as one and the same. A reminder that the most enduring structures are often those built in dialogue with the invisible laws of the world. The quest to build with the earth rather than against it echoes back even further, into the very dawn of European civilization. On the sun-baked island of Crete, the ruins of the palace of Knossos whisper secrets of a people who knew the ground beneath them could turn violent in an instant. This was the heart of the Minoan world, a sophisticated Bronze Age culture thriving in one of the Mediterranean's most seismically active zones. For them, earthquakes were not rare disasters, but a persistent fact of life, a force woven into their mythology, and as we now see, into the very bones of their architecture. Their solutions were not grand theoretical statements, but practical, embedded innovations that reveal a profound, hands-on understanding of how to make stone behave like something alive. Within the labyrinthine walls of Knossos, Archaeologists have uncovered a simple yet brilliant technique known as timber lacing. The Minoan builders did not simply stack their stone blocks. At regular intervals, they would lay long, horizontal wooden beams directly into the courses of the masonry, embedding them within the stone walls. To the untrained eye, these beams might look like mere structural supports or part of an ancient scaffolding system left in place. But their true purpose was far more dynamic. These wooden members acted as flexible ties, stitching the stonework together from within. Think of a brick wall suddenly having a grid of rubber bands running through it. When an earthquake's tremors began to twist and pull at the masonry, the rigid stones wanted to shift and separate. The timber lacing, however, held them in a flexible embrace. The wood could bend, it could stretch minutely, it could absorb the shearing forces that would otherwise cause a rigid wall to crack and tumble. It was a literal reinforcement, not with rigid iron, but with flexible, forgiving organic material. The entire wall became a composite structure, combining the compressive strength of stone with the tensile flexibility of wood, allowing it to sway as a unified, resilient skin. This was not a decorative afterthought. It was a deliberate seismic dampener built into the fabric of the palace. But the Minoan genius extended beyond the walls themselves to the very layout of their grand complex. The Palace of Knossos is famously a maze of rooms and corridors, but it is punctuated by large, open central courtyards and strategic vertical shafts known as light wells. These were not just architectural flourishes for air and illumination. Modern engineers analyzing the plan see a potential early example of what we now call a soft story design. In a multi-story building, a soft story is a level that is significantly more flexible or open than the ones above it, often with fewer walls. During an earthquake, this flexible story is designed to deform in a controlled manner, absorbing the brunt of the energy and protecting the more rigid upper floors. The open courtyards and light wells at Knossos may have functioned in a similar spirit. They created zones of intentional flexibility within the otherwise dense masonry complex. When seismic waves hit, these open spaces could compress and distort slightly, acting as sacrificial buffers that took the strain, preventing a catastrophic failure from propagating through the entire palace. It was a way of designing weakness to preserve strength, of allowing the structure to breathe and buckle in predetermined, non-fatal ways. Here, in the Bronze Age, over 3,000 years ago, we find a civilization not cowering before the Earth's power, but engaging with it through clever, pragmatic design. The timber lacing and the strategic open spaces of Knossos are quiet testaments to a forgotten dialogue between humanity and tectonics, proving that the drive to build something lasting is eternally intertwined with the need to learn how to bend. High in the rugged Caucasus Mountains, another stone song of resilience was being carved into the landscape. Medieval Armenian churches, often perched on remote, rocky outcrops, present a puzzle. In a region torn by countless earthquakes over the centuries, how have these solemn, compact structures of stone endured when so much else has fallen? Their secret is not found in a hidden layer or a flexible joint, but in a brilliant geometric trick hidden in plain sight, right at the transition from wall to dome. The challenge these architects faced was fundamental. How do you gracefully place a round dome, a symbol of the heavens, onto a square base, the footprint of the earthly church? The obvious solution of using 4 arches to create an octagon was known, but the Armenian masters refined this idea into something far stronger and more elegant, the squinch. Look up into the upper corner of one of these ancient churches. You will see a small, curved vault or a series of stepped stone arches bridging the corner of the square room. This is the squinch, a humble but mighty triangular wedge of masonry. Its purpose is deceptively simple: to cut off the corner of the square, creating an 8-sided surface upon which the dome's circular base can more easily rest. But its true genius is structural. Each squinch acts as a powerful diagonal brace. When the dome's immense weight pushes down, the squinches channel that force not straight down, but diagonally outward, directing it precisely into the four massive corner pillars of the church. These pillars, often the thickest and most robust parts of the entire structure, are perfectly positioned to receive this load. The entire building becomes a geometric net of forces, a rigid, interlocked framework where weight follows a deliberate, reinforced path from the heavens to the solid earth. This is what allowed these churches to resist the lateral, shaking forces of an earthquake so effectively. When the ground lurched sideways, trying to twist the square base out from under the dome, that rigid network of squinches and corner pillars held firm. The seismic energy met a unified, triangulated skeleton that refused to deform. The form itself was the reinforcement. This geometric intelligence was amplified by the church's overall shape. Armenian churches are not sprawling complexes. They are profoundly compact, with a centralized, pyramidal massing. The walls rise from a broad base to a narrower drum supporting the dome, creating a silhouette that seems to grow organically from the mountain itself. This shape deliberately lowers the center of gravity, making the entire structure incredibly stable. Much like a wide-based pyramid is far harder to topple than a slender tower. The combination was in seismic intuition, where every line of the architecture followed the invisible lines of force. It was a philosophy where beauty was not applied decoration, but the direct expression of structural truth and enduring strength. Across the Atlantic, a different kind of pyramid rose from the jungle floor. The monumental stepped pyramids like the Pyramid of the Sun at or El at, have long been seen as symbolic mountains, bridges to the celestial realms. But their true genius may be rooted far more deeply in the earth itself. These were not solid piles of stone, they were sophisticated seismic sinks, engineered to swallow the energy of an earthquake and dissipate it harmlessly into the ground. Their iconic shape is the first clue. Unlike the smooth-sided pyramids of Egypt, pyramids are built in distinct, receding tiers. Each level is a massive trapezoid, with walls that slope dramatically inward. This was not merely an aesthetic choice, it was a calculated defense. The wide base provides an incredibly stable footprint, resisting overturning. More importantly, that inward slope creates a natural funnel for forces. When seismic waves hit, the energy travels up the slanted faces and is directed inward and downward, channeled back toward the pyramid's core and its massive foundation, rather than being amplified upward toward the fragile temple at its peak. It is architecture that literally grounds itself. The builders amplified this effect through a clever choice of materials. While the outer shell was often faced with heavy, durable stone, the immense core of the pyramid was frequently filled with a lightweight, porous volcanic rock called. This was of material science. By using this lighter rubble for the interior, they achieved enormous volume and mass, critical for stability, without creating a top-heavy monolith. During an earthquake, the inertial force a structure experiences is directly related to its weight. A heavier pyramid would develop greater destructive momentum as the ground shook beneath it. The core allowed them to build a mountain-scale structure that was, relative to its size, surprisingly light on its feet. The energy from the tremor was absorbed by the porous, crushable interior rubble, which could compact and settle slightly without collapsing, while the rigid outer shell maintained the sacred form. This combination of intelligent geometry and selective material use transformed these spiritual monuments into some of the most stable structures ever conceived. They were not fighting the earthquake, they were absorbing it, using their own monumental form to sink the violence of the tremor deep into the welcoming earth. This holistic approach to resilience, where symbolism and structural science were indistinguishable, stands as one of humanity's greatest architectural achievements. Yet if these ancient cultures from Japan to Armenia to all possessed such profound and effective knowledge, a troubling question remains. Why did this wisdom, tested and proven over, seemingly vanish from the world's collective memory? For centuries, the slender stone finger of a minaret points silently toward the sky, a symbol of faith and a masterpiece of seismic isolation. In the great Ottoman mosque complexes of Istanbul, like the Magnificent, architects faced a unique structural dilemma. They needed to place these incredibly tall, slender towers directly adjacent to the vast, heavy bulk of the central prayer hall and its enormous dome. If both structures were rigidly connected on a shared foundation, an earthquake would spell disaster. The different rhythms of the two buildings, the quick, high-frequency sway of the slender minaret and the slower, deeper roll of the massive dome, would clash violently. They would begin to beat against each other, each structure amplifying the other's motion until one or both shattered in a catastrophic feedback loop. The Ottoman solution was a stroke of brilliant compartmentalization. They gave the minaret its freedom. When you look at these grand complexes, you are not looking at a single monolithic building. You are looking at a carefully orchestrated ensemble of independent structures, each with its own role and its own path to survival. The minarets were not simply extensions of the mosque's walls. They were built upon their own deep, independent foundations, completely separate from the footings of the main prayer hall. A hidden gap, a seismic moat, existed beneath the surface between them. When the ground began to tremble, this design allowed each element to dance to its own natural rhythm. The heavy central dome would sway with a ponderous, low-frequency roll. The slender minaret, just a few meters away, would flutter with a faster, more delicate vibration. Crucially, because they were not locked together, these rhythms could not couple. They could not grab hold of one another and start that deadly, amplifying tug-of-war. The minaret swayed in its own space, the mosque swayed in its own, and the earthquake's energy was dissipated in two separate, non-interfering systems. This is a profound lesson in preventing cascade failure. In a rigidly connected complex, the collapse of one key element, like a minaret crashing sideways, could easily trigger the collapse of the entire structure. By decoupling them, the Ottomans ensured that even in a worst-case scenario, damage could be contained. One element might fail, but it would not necessarily doom its neighbor. This philosophy of intelligent separation, of allowing components the freedom to move independently, mirrors a very modern principle in engineering, from seismic gaps in bridges to the isolation of mechanical systems in skyscrapers. It reveals a mindset that thought not just about strength, but about the graceful management of failure, ensuring that a tremor would not become a total catastrophe. Stone and wood alone could not ensure 1,000 years of survival. The most critical component in this ancient equation was not a material or a geometric principle, but something far more human, a continuous, unbroken thread of care. These temples endured not solely because they were brilliantly engineered, but because they were profoundly loved. They were woven into the daily, seasonal, and spiritual rhythms of the communities that built them, and that ongoing relationship became their most powerful maintenance program. Regular rituals, annual festivals, and sacred pilgrimages were not just spiritual exercises, they were practical acts of structural stewardship. Before a major festival, the community would not simply decorate, they would inspect. Priests, artisans, and local builders would walk the perimeter, checking the foundation stones, examining the wooden joints, and assessing the roof tiles. A loose stone was reset. A cracked beam was braced or replaced. Erosion from rain was repaired. This was not emergency work following a disaster. It was preventative care driven by cultural imperative. The temple had to be perfect for the gods, and that meant it had to be physically sound. This cycle of ritual and repair created a powerful feedback loop. Smaller tremors, the kind that might cause minor, incremental damage, were addressed long before that damage could accumulate into a fatal weakness. A hairline crack from one season's quake was sealed before the next monsoon could widen it. A slightly shifted column base was realigned before its uneven load could stress the entire portico. The community, through its traditions, was performing constant, non-destructive testing and proactive intervention. The structure was never allowed to fall into a state of neglect where a single major event could be catastrophic. It was always kept in a state of readiness, its resilience constantly renewed. This transforms our understanding of these buildings from static monuments into dynamic, living entities. They were not museum pieces frozen in time. They were participants in an ongoing conversation between people, place, and purpose. The temple's longevity was a shared project, a covenant between the builders and countless generations of caretakers who followed. This cultural practice embedded a simple, vital truth into the stone, that vigilance is not a one-time event, but a perpetual tradition. It highlights a lesson modern engineering often overlooks at its peril. The finest design in the world can still fail without a committed, watchful eye. Our strongest systems require not just brilliant creation, but devoted, unending stewardship. Yet for all its brilliance, this deep conversation between humanity and the earth fell silent for centuries. The industrial age brought new materials and a new philosophy, one of rigid domination over nature. We built with steel and concrete, believing sheer strength could defy any force. Then, in the final decades of the 20th century, a violent tremor delivered a humbling lesson. The Great Earthquake struck the city of Kobe, Japan, in January of 1995. It was a catastrophe of the modern age. The shaking lasted just 20 seconds, but it collapsed elevated highways, toppled contemporary buildings, and claimed over 6,000 lives. Amidst the devastation, however, stood quiet, resilient witnesses. While modern infrastructure lay in twisted ruins, many of the region's centuries-old wooden temples and pagodas remained standing, their roofs intact, their central pillars still pointing toward the sky. They had swayed through the same terrifying forces and survived. For engineers surveying the damage, this was not just a historical curiosity, it was a profound professional shock. The most advanced seismic codes of the time had failed in ways that ancient, seemingly primitive carpentry had not. It became an undeniable stone and timber indictment of modern assumptions. This seismic event did more than shake the ground. It shook an entire discipline, forcing a fundamental question: had we, in our pursuit of technological mastery, forgotten a more profound wisdom written in wood and stone? The answer launched a quiet revolution, a deliberate turning back to look forward. This wake-up call sparked a fascinating new collaboration, a fusion of fields that had long operated in separate worlds. Archaeologists, who study the artifacts of the past, began working hand in hand with structural engineers, who design the buildings of the future. This new discipline is called. Its mission is to read the built environment like a historical text, searching for the subtle signatures of seismic adaptation. Researchers now examine ancient structures not just for their artistic or cultural meaning, but for their hidden engineering logic. They use laser scanners to map the precise angles of Inca stonework, searching for the geometric rules that distribute stress. They create sophisticated computer models to simulate how a hanging in a pagoda dampens vibrations. They analyze the chemical composition of Roman concrete, seeking to reverse engineer its self-healing properties. This is not mere academic curiosity, it is a practical salvage operation. The goal is to decode these time-tested, often low-tech solutions and translate them for a world that desperately needs sustainable and resilient construction. The ancient world, it turns out, may hold the blueprints for a safer future. The most direct result of this rediscovery is the realization that modern engineering has been, in many cases, reinventing the wheel. When contemporary designers developed base isolation systems in the 1970s and 80s, using layers of rubber and steel to let a building slide on its foundation, they were celebrating a groundbreaking innovation. Yet, the concept was already old, perfected in the sliding stone spheres under Japanese pagodas and the gravel beds beneath Greek temples. The massive tuned mass damper in the Taipei 101 tower, that golden sphere swaying to counteract wind and tremors, is a direct, high-tech descendant of the intentional dead weight in a Chinese temple roof. Our most advanced seismic solutions are often elegant, expensive mechanizations of principles that ancient builders implemented with elegant simplicity. This is not to diminish modern science, but to highlight a stunning convergence, where cutting-edge computer modeling arrives at the same conclusion as a master carpenter observing a bamboo grove in a storm. Resilience through flexibility, harmony with motion, these are not new ideas. They are ancient truths, patiently waiting in the stones of forgotten temples for us to remember. The true magic of these structures often lies hidden in the glue. While we marvel at the stones and timbers, the ancient builders' most guarded secrets were sometimes written in the very mortar that held it all together. This was not the brittle, rigid cement we know today, but a form of material alchemy, a forgotten chemistry of resilience. Across the world, master masons developed special recipes that gave their buildings a living, breathing quality, an ability to endure that modern materials struggle to match. In ancient India, for example, builders achieved a legendary bond by mixing standard lime mortar with a surprising ingredient, a slurry made from sticky rice. This wasn't a mere additive, it was a transformative agent. The complex carbohydrates in the rice created a dense, networked matrix within the mortar as it cured. The result was a binding material that was incredibly strong in compression, yet retained a subtle, organic flexibility. It could absorb tiny shifts and settle without shattering, allowing hairline cracks to form and then seal themselves through a slow, ongoing chemical process. This was a mortar that worked with the building's natural movement, not against it. Half a world away, in the dry climates of, builders turned to the local flora for their resilience. They extracted the sap from the prickly pear cactus, known as nopal, and blended it into their plasters and mortars. This viscous liquid acted as a natural polymer, a kind of ancient superglue. It not only improved adhesion and water resistance, protecting structures from the elements, but it also imparted a degree of plasticity. A wall finished with this plaster could withstand minor ground settlement and thermal expansion without developing the large, destructive cracks that plague rigid modern materials. This soft chemistry represents a fundamental philosophical difference. Today's Portland cement aims for a final, unchanging state of maximum hardness. But these ancient recipes aimed for a state of durable adaptability. They created materials that were dynamic, that could sustain micro-damage, the tiny, inevitable fissures from small tremors or settling, without allowing that damage to propagate into a catastrophic failure. The micro-crack would form, and then the chemistry of the material itself would begin to work, slowly filling the gap with new crystalline growth or simply holding the fracture in a flexible embrace. This added a crucial, often invisible layer of resilience to the entire structural system. It meant the building's skin and joints possessed a kind of immune response, a capacity for self-repair at the microscopic level. It was a final, elegant line of defense, ensuring that the brilliant dance of the large-scale structure was supported by a chemistry that knew how to bend. The most stable shape is not always the most perfect one. Walk into a temple that has stood for 1,000 years, and you might feel a strange, almost subconscious sense of imbalance. A column here seems a hand's width out of place. The spacing between pillars on the north side appears subtly different from the south. At first glance, it seems like a builder's error, a flaw in an otherwise sacred geometry. But what if that flaw was the point? This is the counterintuitive world of seismic asymmetry, where a calculated imperfection could mean the difference between standing and shattering. For generations, we assumed the goal of sacred architecture was perfect symmetry, a mirror image reflecting cosmic order. Yet in earthquake zones around the world, the temples that survived often carry these quiet, deliberate irregularities. Scholars now believe these were not mistakes, but a sophisticated form of vibrational defense. Think of a tuning fork. Strike it, and it vibrates at a single, pure frequency. Now imagine an entire temple built with perfect bilateral symmetry. When a seismic wave hits, that wave finds a structure that is, in essence, a giant stone tuning fork. Every matching element on the left and right is identical in mass, height, and spacing. This allows the energy to flow through the building in a synchronized, amplified wave. The entire structure can begin to sway in a terrible, unified rhythm, each side reinforcing the motion of the other, building force until something gives way. It is the architectural equivalent of soldiers marching in step on a bridge, risking a catastrophic resonance. The ancient solution was brilliantly simple: break the step. By introducing a subtle asymmetry, perhaps by shifting one column slightly off its expected axis, or by varying the spacing between a pair of pillars, the builders introduced what engineers call a detuning element. They disrupted the perfect mirror. Now, when the seismic energy enters the structure, it encounters a slight dissonance. The left side and the right side no longer have identical natural frequencies. They want to sway at slightly different rhythms. This internal mismatch prevents the building from locking into that single, destructive harmonic. The energy is scattered, becoming a conflict of small, counteracting motions within the structure itself, rather than a unified force tearing it apart. It is the difference between a choir singing one powerful, sustained note that shatters glass, and a group of people humming different, slightly discordant melodies. The focused power is lost. This principle can be seen in surviving Greek temples, where column spacing often varies, and in some Japanese pagodas, where the central pillar is deliberately not perfectly centered. The builders seem to understand that true resilience sometimes requires a break from perfect order, a willingness to introduce a controlled chaos to defeat a greater chaos. It suggests a humility before nature's power, an acknowledgement that to survive the Earth's unpredictable song, a building must be slightly out of tune. A temple's design never answered just one question. The same feature that allowed it to dance with an earthquake might also be the very thing that let it breathe through a monsoon or endure a century of scorching sun. This was the genius of multifunctional design, where every architectural choice served several masters of survival at once. Consider the iconic, sweeping roofs of temples across Southeast Asia and Japan. Their deep, dramatic overhangs are a direct response to the relentless monsoon rains. They act as giant umbrellas, casting water far away from the delicate wooden walls and paper screens below, preventing rot and erosion. But that same massive, projecting roof does something else of equal importance. It dramatically lowers the entire structure's center of gravity. All that weight, the heavy clay tiles and the intricate wooden framework, is perched high up and pushed outward. This creates a powerful inertial anchor, making the building incredibly resistant to being tipped over by the lateral shove of an earthquake. The roof was not merely a shelter from rain, it was a pendulum weight for stability, a single solution born from a dialogue with two very different environmental forces. Similarly, in the arid deserts of the Middle East and North Africa, you find temples and homes with extraordinarily thick walls. These massive barriers of mud, brick, or stone were first and foremost a thermal strategy. Their immense thermal mass absorbed the fierce heat of the day slowly, keeping interior spaces cool, and then released that stored warmth gradually during the cold desert nights, acting as a natural climate battery. Yet, this thickness served a dual, seismic purpose. Inertia, the tendency of a massive object to resist changes in its motion, is a building's friend during a tremor. A thin, lightweight wall is easily thrown off balance and shattered by seismic waves. But a wall several feet thick possesses enormous mass. When the ground lurches, that wall's sheer inertia makes it sluggish to respond. It resists the initial jolt. The earthquake's energy must work much harder to set such a heavy element into destructive motion. The thick wall, designed for temperature moderation, becomes a formidable inertial damper against shaking. This principle of synergy extended to ventilation. The wind catchers and clever courtyard layouts of Persian architecture, designed to funnel cool breezes into buildings, also created open, flexible spaces within the structural grid. These zones of intentional openness could deform slightly during a quake, acting as the controlled, flexible joints we see in other traditions. The design answered the need for cool air and for seismic flexibility with the same graceful geometry. This holistic philosophy reveals a deeper truth about these ancient builders. They did not see environmental threats as separate items on a checklist to be solved one by one. They viewed their world as an interconnected system. A building was an organism existing within a specific climate and geology, and every part of its design had to help it thrive in that complete environment. The result was not just a temple that could survive an earthquake, but one that could also weather 100 monsoons, 1,000 desert, and the slow creep of seasonal decay, all with the same integrated set of features. This was resilience built into the very DNA of the form, a testament to designing not just for disaster, but for life itself. The resilience of a temple was not locked in a vault or written in a manual. It was carried in the minds and hands of the builders themselves, passed from master to apprentice in a sacred, unbroken chain. This was the human heartbeat of the entire system, a living library of knowledge that thrived for centuries without a single formal blueprint. The transmission of this complex engineering wisdom relied on two profound pillars: the rigor of the apprenticeship and the poetry of oral tradition. A young learner would not start with theory, but with observation and repetition. For years, they would perform the most humble tasks, mixing mortar, fetching stones, and watching the master's every move. This immersion was not busywork, it was sensory education. They learned the feel of a properly balanced stone, the sound of a well-struck chisel, the subtle give of a timber joint that was tight enough to hold but not so rigid it would snap. Through this daily, hands-on dialogue, the apprentice absorbed the master's intuition, the deep, almost instinctual understanding of how materials behaved under stress. The principles were not taught as abstract laws of physics, but as practical rules of thumb passed down in simple, memorable phrases. A master in Greece might instruct, "The stone must sleep as it lay in the mountain," teaching the apprentice to place each block in its natural, most stable orientation. A carpenter in Japan might say, "The joint must breathe with the wind," encoding the principle of flexible joinery into a poetic directive. These were more than tips, they were condensed packages of seismic wisdom. In some cultures, this knowledge was even set to music. Builders used rhythmic construction songs or chants that coordinated the labor of large teams. The tempo of the song would dictate the pace of work, ensuring a steady, harmonious effort. But the lyrics themselves often contained coded instructions about proportions, sequences, or critical alignments. Singing the song was remembering the rule, turning a complex engineering procedure into a communal melody that everyone on the site knew by heart. This oral and practical tradition created an incredibly robust, adaptable system of knowledge transfer. It was a living library, constantly updated and refined with each new project and each new tremor that tested their work. The library was not in a building, it was in the community. This is what makes the loss of this knowledge so profound. The chains of transmission, so carefully forged over generations, were fragile in the face of historical upheaval. Periods of colonization often suppressed indigenous building traditions, imposing foreign styles and materials. The relentless march of industrialization prized speed, standardization, and new technologies over slow, craft-based methods. The devastation of war could erase not just buildings, but the very masters who held the knowledge, scattering apprentices and silencing the songs forever. When the master dies without passing on the song, the library burns. This is the tragic side of the story, the reason why this profound seismic wisdom became forgotten. It wasn't lost to time through mere neglect. It was often severed by forces that disrupted the human relationships at its core. Our modern quest to understand these ancient techniques is, therefore, a form of archaeological detective work. We are left to reverse engineer the wisdom from the silent stones, piecing together the rules of thumb from the proportions of a wall, inferring the forgotten songs from the rhythm of the joints. We are trying to reconstruct the library from the few surviving books, a painstaking process that highlights an invaluable lesson. The most advanced engineering is worthless without a culture committed to preserving and passing it on. The ancient master's intent is now being read by machines. We are no longer limited to measuring tapes and educated guesses. A technological revolution in archaeology is giving us eyes that can see through jungle canopies and hands that can measure with laser precision, all without disturbing a single sacred stone. This is the era of digital archaeology, and it is finally cracking the code of those ancient seismic blueprints. At the forefront is a technology called LiDAR, which stands for light detection and ranging. Mounted on planes or drones, these laser scanners fire millions of invisible pulses of light at the ground below. By measuring the time it takes for each pulse to bounce back, they can build a staggeringly detailed three-dimensional map of the Earth's surface, digitally stripping away dense vegetation to reveal the hidden contours of forgotten foundations, roadways, and entire city layouts. For the first time, we can see an ancient temple complex not as a collection of ruins, but as a complete engineered landscape. We can map the subtle drainage channels that prevented water from undermining the base, or trace the precise alignment of walls that may have been designed to break seismic waves. This digital twin becomes a perfect, immutable record, a baseline from which all analysis begins. But the map is just the beginning. To understand how these structures behaved, we need to see them move. This is where artificial intelligence enters the conversation. Engineers can feed these hyper-accurate digital models into sophisticated simulation software. The AI can then apply virtual seismic forces, mimicking the exact frequency and intensity of historical earthquakes known to have struck the region. We can watch, in accelerated time, as the digital temple sways. We can see where stress concentrates, which joints flex first, and how the energy travels through the network of stones and timbers. The AI acts as a time machine for physics, allowing us to run thousands of simulations in minutes, testing which design features are merely decorative and which are absolutely critical to survival. This process of virtual stress testing is a form of high-tech reverse engineering. It allows researchers to isolate variables. For instance, they can digitally remove the hanging central pillar from a Japanese pagoda model and rerun the earthquake simulation. The result is often a dramatic, catastrophic failure on screen, visually proving the pillar's indispensable role as a tuned mass damper. They can alter the friction coefficient between the stones in an Inca wall, watching how the energy dissipates differently. This technology translates the master builder's empirical wisdom, gained through trial and error over generations, into clean data sets, stress graphs, and mathematical formulas. A rule of thumb passed down through song, like the joint must breathe, becomes a quantifiable principle of dynamic damping with a precise coefficient of friction. This is the profound bridge being built between the ancient and the modern. The intuitive genius carved in stone is being translated into the algorithmic language of contemporary engineering. It means the lessons of the Bronze Age can now directly inform the building codes of the 21st century. We are not just preserving these temples as museum pieces, we are downloading their operating manuals. A temple's deepest secrets are buried in its foundations, but to unearth them risks destroying the very legacy we seek to understand. This is the quiet crisis at the heart of modern archaeology, a delicate dance between the hunger for knowledge and the duty of preservation. Imagine knowing that beneath the floor of a 1,000-year-old pagoda lies a perfectly carved stone sphere, the key to its seismic isolation. The scientific urge is to dig, to measure, to hold the artifact and decode its every property. Yet, the act of excavation is inherently destructive. To reach that sphere, you must dismantle centuries of stratified history, disturb the delicate equilibrium of soils and stones that have settled into a stable embrace, and potentially introduce new points of weakness into a system that has proven its resilience. It is a profound ethical dilemma, forcing us to ask whether understanding how it worked is worth the risk of ensuring it never works again. This tension defines the field today, transforming how we interact with these ancient teachers. The old model of archaeology, which often prized discovery over conservation, is giving way to a new ethos, one that treats every monument as a patient rather than a puzzle. The primary directive has become, first, do no harm. This principle has sparked a revolution in destructive testing. Instead of breaking open walls, researchers now use ground-penetrating radar to map subsurface features, sending harmless radio waves into the earth to create a sonogram of hidden foundation layers. Thermal imaging cameras can detect subtle variations in surface temperature, revealing hidden voids or moisture paths that indicate structural composition. They employ ultrasonic testing, similar to medical sonograms, to assess the integrity of stone and mortar from the outside, listening for the echoes that reveal internal cracks or densities. These tools allow us to peer inside the body of the temple without making a single incision. The data they gather is then fed into the virtual models we discussed, creating increasingly accurate digital twins. We can run our seismic simulations not on guesswork, but on scanned realities. This approach represents a fundamental shift in perspective. We are no longer just extracting information from these sites, we are in a dialogue with them. The goal is to learn from their continued existence, to observe how they age, how they settle, and how they respond to minor, ongoing environmental stresses. This long-term observation can be more valuable than a single, disruptive analysis, because it reveals the structure as a living system. The ethical path forward, then, is one of humility and technological restraint. It acknowledges that some secrets are meant to stay buried, that the ultimate testament to the builder's genius is not in our complete understanding, but in the enduring, silent performance of their work. Our responsibility is to be meticulous stewards, using our most advanced tools not to dissect, but to listen, ensuring these stone sentinels remain standing, not as hollow shells in a museum, but as functioning monuments that can whisper their lessons to the centuries yet to come. The silent conversation between ancient stone and modern steel is finally beginning. We stand at a remarkable crossroads, where the deepest lessons from the past are meeting the most advanced tools of the present, not to replicate the temple, but to reinvent the skyscraper. The ultimate goal is a profound synthesis, a fusion of timeless principle and cutting-edge innovation that could reshape our cities from the ground up. This is not about nostalgia. It is about creating a new hybrid intelligence for the built environment. Think of a future urban tower, its glass and steel facade gleaming in the sun. Within its sleek exterior, however, beats a heart of ancient wisdom. Its skeleton might not be rigidly bolted, but designed with flexible, jointed connections inspired by the intricate wooden brackets of a Japanese pagoda, allowing the entire frame to sway as a unified, shock-absorbing organism during a tremor. Its foundation could sit not on a solid concrete slab, but on a modernized version of a Greek or Roman isolation bed, using engineered layers of recycled gravel and composite materials that slide and generate friction, harmlessly dissipating seismic energy before it ever reaches the living floors above. We might even see buildings with intelligent, weighted roofs or internal pendulums, direct descendants of the heavy temple roof and the hanging, but now made of advanced alloys and guided by sensors that tune their counter swing in real time to the earthquake's exact frequency. This fusion extends beyond earthquakes alone. The ancient principle of multifunctional design, where one feature solves for climate, structure, and resilience simultaneously, is a blueprint for sustainability. A building's shape could be optimized to channel wind for natural cooling, while its very form and material mass are calculated to dampen seismic forces. The self-healing chemistry of Roman concrete or sticky rice mortar inspires research into new bioconcrete, embedded with bacteria that precipitate limestone to automatically seal cracks, giving structures a literal immune system. This is the promise, a new paradigm of architecture that is resilient, sustainable, and deeply informed by cultural ingenuity. It moves us from buildings that are merely strong to buildings that are intelligently alive, in constant, graceful dialogue with the forces of the earth. They would not just occupy space, they would respond to it, honoring the past not through imitation, but through evolved understanding, creating legacies of safety that could stand for to come. These temples were not built to defy the earth, but to listen to it. From the polygonal walls of the Incas to the swaying pagodas of Japan, we have walked through a hidden history of human ingenuity, a conversation in stone and timber that lasted for. The forgotten seismic engineering of these sacred spaces offers a single, transformative lesson that true resilience is rarely found in rigid resistance. It is discovered in intelligent flexibility, in a profound harmony with natural forces, and in a philosophy of holistic design where every element, from the deepest foundation to the hanging ornament, plays a part in a unified dance of survival. These structures are far more than beautiful relics of a distant past. They are active repositories of knowledge, their silent stones holding blueprints that are urgently relevant to our own earthquake-vulnerable world. We live in an age of incredible material strength, yet our cities often remain brittle in the face of planetary forces. As we confront the dual challenges of a changing climate and rapid urbanization, the pressure to build quickly and cheaply can overshadow the imperative to build wisely and lastingly. In this context, the quiet wisdom of the ancients speaks directly to our modern dilemma. They remind us that sustainability and resilience are not expensive add-ons, but the very foundation of intelligent creation. They achieved monumental endurance not with limitless resources, but with deep observation, clever material science, and a cultural commitment to stewardship that spanned generations. Perhaps then, the most progressive path forward is not always to invent something entirely new, but to remember. It is to look back with fresh eyes and curious minds, to rediscover the principles of yielding strength and integrated design that have been patiently waiting in the stones. This is not about abandoning technology, but about enriching it with a deeper, more ancient kind of intelligence. The next time you see a skyline of gleaming towers or walk through the echoing hall of an old stone building, let a question linger. What timeless conversation about balance, motion, and endurance might be waiting there, ready to be heard again? If this journey into the mind of the ancient builder resonated with you, we would love to hear your thoughts in the comments below. And for more explorations into the hidden genius of our shared past, be sure to subscribe.